In this video, we're going to be looking at surface area. And before we get into the actual math of it, I want you to just think about a couple real-life examples that I'm sure you've seen. First of all, wrapping presents at Christmas or a birthday or whatever. The idea being that you need to find out how many square inches of paper you need to cover that particular object. Now, it might not always be a box. It could be also a cylinder or some other random size or shape. But the point is the same, that you have to cover that object completely. And so too, when we also look at the example of painting a room, we see that each wall has its own dimensions, but the idea is still the same, that we need to cover each wall with a certain amount of square footage of paint. The main idea behind both of these is the idea of paneling, or faces, where you try to solve a subproblem, multiple subproblems, and then bring it back together to add it all up and find the total area. Some tools that we're going to need. We recall the area of a rectangle is base times height. The area of a triangle is half base times height. And the area of a circle is pi r squared. As I mentioned, when we break these shapes down into panels, it's really just going to be a matter of solving the area of these basic 2D shapes. So let's start off with the most basic example, a box, or more formally, a rectangular prism. We've been given the dimensions of width is 10 inches. Length is 12 inches, and height is 6 inches. Some books, some terminology might also use base instead of width and depth instead of length, but the idea is still the same. What I tried to do is color one of the two pairs in each, or excuse me, one of the pairs in each set a distinct color. So on the back and the front we'll have red, the sides will be represented by yellow, and the bottom and the top will be represented by blue. So when we break it down into subproblems, then it looks a lot easier. So now it's just a matter of solving this face, and this face. And we've been doing that for a while. So area is base times height, 10 times 6, 60 square inches. Base times height, 10 times 12 is 120, 120 square inches. And 12 times 6, 72 or 72 square inches. And we remember that it's not just one face that these are representing, but two, right? There's a back and a front, a left and a right, a bottom and a top. And so for each of these, we actually need to double. So 2 times 6 is 120, 2 times 120 is 240, and 2 times 72 is 144. Adding all those up, we get 504 inches squared, or 504 square inches, however you prefer to label that. Okay, moving on to something slightly more complicated, a cylinder. We don't just have nice rigid edges anymore. We have these faces, these circular faces on the front and back, and then this tubular part, right, the wraparound space, whatever you want to call that, the midsection. And we need to try to figure out how much square centimeters are needed to cover this entirely. We're given a height of 10 of this cylinder. We're told the radius is 6, and that doesn't seem like a lot of information, but we've learned in the past that when dealing with circles, even by just being given the radius, you can find out a lot about a circle. Okay, so we know that if the radius is 6, that means the diameter is 12. And then we have this odd shape, and up here there was no rectangle, so where am I getting this from? Well, if you think about it, if we take this red height line and we cut, just imagine taking these faces off for a second. So if we remove these, right, if we remove those and just look at the tube, and we cut along this height line and we unwrap it, what would we have? We would have a rectangle. And what would be the dimensions of that rectangle? Well, the base would be what we just cut along, the height, right? This would be that red line. And the new height would be what? Well, it would actually be the circumference of the circle. Okay, and that's where that C is coming from. And we'll find out how to calculate that in just a minute. Okay, first of all, looking at the circles, right, the top and the front and the back, top, bottom, we're told the radius is 6. Again, the area of a circle is pi r squared. Pi times 6 squared is 36 pi. And we're just going to leave it in terms of pi. If you want to approximate pi to 3.14 or 22 over 7, that's fine. I think it looks cleanest just leaving it as pi. And then remember that the circumference over here, the circumference of a circle is pi d, pi times the diameter. So what we're going to do is substitute in for d 12, right? Because we found out that up here the diameter was 12. So instead of base times height, now it's 10, because remember the height was 10, times c, and now c is pi times d, or 12 pi. So now we have the area of this whole figure is 120 pi. Okay? So now we remember, because we're dealing with two circles, we have to multiply it by 2, front and back. So we do 2 times 36 pi, that's 72 pi. Over here we have 120 pi. So we add 72 pi plus 120 pi, which is 192 pi centimeters squared. Okay? So again, just to review, we started with this cylinder shape, and we broke it down into its pieces. We have the front and back faces, and then we have that midsection. Okay? And the key thing is to recognize that that midsection can be broken down into a rectangle by cutting it open and rolling it out. Once we do that, like I said at the beginning of the video, we're just back to basic shapes, rectangles and circles. Okay? And that's pretty much how all cylinder problems go. Finally, we have a triangular prism. Okay? And again, when you hear prism, just think of some shape, in this case a triangle, being stretched, right, or being extended, right? We have our triangle, then we extend it out to another triangle. And always with prisms, the case will be that when you stretch or expand or extend, the shapes that connect those two shapes are always going to be these panels, these rectangular panels, okay? Now when it's all one color, it's not really clear. I was going to do the faces like I did for the other ones where I colored it in, but I thought it would be more helpful to actually just think of the outsides. Okay, so we notice we have red, blue, yellow, green, and then what we're going to be able to do is break that down into multiple subproblems. So let's just look at our dimensions first. For this triangle up front, we have 6, 8, and 10. For the extension pieces that make the long panels, each of these is 20. So these 3 green bars are 20. And then another key piece that we're given is a perpendicular height line. And remember, the area of a triangle is 1/2 base times height, but you always need to make sure that the height is a line that's perpendicular to the base. So in this case, our base is 10, our height is 4. The height is not 6, the height is not 8, the height is 4. Okay, so we're given everything we need to solve this. Now we're going to take this and we're going to break it off into multiple pieces. Okay, first of all, just solving for that face, I think it's the easiest part to start with. We have 1/2 base times height. Base is 10, height is 4. 1/2, 10 times 4 is 5 times 4, that's 20 meters squared. Okay, and again, as with the other problems, we recognize there's not just one triangle, there's 2. Okay, so we say 2 times 20, that's 40 square meters. So 40 square meters just for this and this, but now we need to deal with these 3 panels, all of distinct size. So what I've tried to do is break them off so we can look at them individually. Okay, so again, we look at this and then look back at the original shape one more time. We should be able to see these 3 panels. Okay, so now let's look at it. And again, we're just back to dealing with basic rectangles. So our base is consistently going to be 20. Our heights vary by 2 each time, right? This is 6, 8, 10. So we have 120, 160, 200. So now we're going to add up all these pieces. 120 plus 160 plus 200 plus the 40 from above, right? That gives us 520 meters squared. Okay? So again, I think it's cool to look through these examples, these 3-dimensional shapes, and realize that we can actually break them down back into simpler 2-dimensional problems. Once we're able to do that, I think it's going to make it a lot easier for us in solving the problems, no matter what numbers are given. As I've said before, no matter what numbers they give you for these, it doesn't make the problem necessarily harder. It might make it more tedious, but they can't make the problem harder, right? Once you know how to solve a box, a rectangular prism, it doesn't get any trickier than this, okay? Same thing with cylinders, same thing with triangular prisms, and really the same thing with any other 3-dimensional object that you see, okay? So that's that for that video. Thank you for watching.